Hello, AP Chemistry. How are we doing today? Hopefully, y'all are doing well. So today we are going to be starting our notes on thermochemistry. And this first unit that we have, this first set of notes that we have is going to be just kind of an introduction, just kind of some reminders of things that you've done in the past with chemistry and thermochemistry. All right. So let's go ahead and get started on this. So first off, what is thermochemistry? Thermochemistry is going to be the study of energy and its changes. And when we talk about thermochemistry, if we talk about energy in chemistry, we're talking about is it gained or lost? And typically we'll talk about it in terms of heat. Okay. Now, energy is going to be the capacity to do work or produce heat. Now, work is typically falling into the category of physics, right? And heat would be falling in the category of chemistry. Now, we do sometimes have a little bit of crossover between both. But that's kind of where we generally focus in terms of energy. Now, when we talk about energy, we do need to keep in mind the law of conservation of energy. And what we know from that is energy can be converted from one form of energy to another, but it cannot be created or destroyed. So if you start with a certain amount of energy, you should also end with that same amount of energy. Okay, so do keep that in mind. Make sure you're not producing these random, like way more or way less, or even a little more, a little less. Because you're going to be, there's something going on if you do. You've either calculated wrong or you're not taking into account something like energy that, for instance, could be inside of a bond or something like that. Okay. Now, when we talk about energy in terms of chemistry, we do tend to focus on three types. Potential energy, which is going to be that energy due to position or composition. So it's pretty much that stored up energy. We talk about kinetic energy, and that's going to be the energy in motion. And again, when we're talking about kinetic energy, that's typically going to be temperature. Because remember, temperature is the average kinetic energy. Now, kinetic energy does depend on the mass and the velocity. And remember that temperature is that measure, again, of average kinetic energy. And then when we're solving for kinetic energy, we can do kinetic energy equals 1/2 mass times velocity squared, where mass is going to be in kilograms, your velocity is in meters per second, and then your units will be joules. All right. And then the other type of energy that we talk about in chemistry is chemical energy, and that's going to be the energy stored in the chemical bonds of a substance. And we'll actually talk about that more and how you solve for the amount of energy in those bonds on our fourth set of notes for this unit. Okay. All right. So energy transfer. So when we're talking about how energy is moving inside of a reaction, for example, we've got two things. We've got the system and we've got the surroundings. Remember, the system is going to be the thing that we're focusing on. So if we're looking at, I took some potassium chloride and I dropped it into water. So I'm looking at that potassium chloride. It is going to be my system. The water would then be the surroundings going on. And so what we'll see is that we could see a change in energy, a change in heat. Okay. Now, heat does involve a transfer of energy from one substance to another, so from one object to another, and that's going to be due to a change or a difference in temperature, and it's always going to be spontaneous. So what is spontaneous? Remember, spontaneous means it does not require any assistance. So, like if I take a block of metal and I drop it into water, and they're the same temperature, so they're both sitting at room temperature, is there going to be a transfer of energy? No. Why not? Well, because they're the same temperature, right? But if we're talking about taking that block of iron and I heat it up to 300 degrees Celsius and I drop it into room temperature water, well, what's going to happen? Well, there's going to be a transfer of energy, right? The energy is going to flow from that block of iron to the water, and probably it'll look a little bit explosive in terms of how it does it, where you drop it in there and then the water would be producing so much gas so rapidly that we would see it actually explode out of there. So in terms of kinetic energy, which would be higher? What if I had a warm substance or a cold substance, which would have a higher kinetic energy? Well, remember that kinetic energy relates to temperature. If I've got a higher temperature, I've got a higher kinetic energy. So in this case, I've got a warm substance and a cold substance. So the warm substance will have the higher kinetic energy than the cold substance will. And so that's what I just wrote right there. So warm substance equals a higher temperature, which equals more particle movement. Okay. Now, what about the second question? When does heat transfer stop? Okay, so remember that your heat transfer is going to continue until we reach thermal equilibrium. Now, that's kind of what was falling into up here. So we are going to see that transfer of energy until we reach thermal equilibrium, which essentially just means their temperatures become the same, where their average kinetic energies are about the same, which means that energy is going to be equally shared amongst all of those substances. Okay. Now, do keep in mind that when we're talking about a change in temperature, to solve for that, you're going to need to do the final temperature minus the initial temperature. And so that's what this says right here. Okay, final minus initial. Okay, so that transfer is going to stop when the substance reaches thermal equilibrium. Heat flows from hot to cold. Okay, so let's take a look at this question here. It says heat transfer and thermal equilibrium. So a metal sphere is heated to 125 degrees Celsius and then placed into a beaker of water with an initial temperature of 35 degrees Celsius. How would the kinetic energy of the molecules in the sphere change? Well, the kinetic energy would decrease in the sphere. Why? Because energy is going to leave the sphere and go into the water. So for the sphere, your kinetic energy will decrease. What about for the water molecules? So for the water, your kinetic energy is going to increase. And again, remember, kinetic energy is going to be that average, it's going to be temperature, right? So your temperature is going to be your average kinetic energy. So you'd see the increase in temperature of the water, decrease in temperature of the sphere, okay? And then the beaker of water reaches thermal equilibrium at 52 degrees Celsius. What does this tell you about the thermal energy of the metal sphere and the water? Well, looking at that, what do we see in terms of that transfer of energy? How did our temperature change? Well, from the sphere to the thermal equilibrium, we went from 125 down to 52. So 125 minus 52, so our temperature changed by a total of 73 degrees, right? Whereas the water went from 35 to 52. So that temperature is going to change by 17. So what did we see? Well, we see that the metal dropped a lot faster than the water. So the water was actually able to absorb more energy and before increasing its temperature. So when we think about that, that falls into, remember, specific heat. That's the energy required to change 1 gram of a substance by 1 degree Celsius. So what that tells me is that water has a higher specific heat, a much higher specific heat than the metal sphere. Okay? All right. So work. Again, we do tend to focus on this when we're in physics, but we do need to know a little bit about work. So I am just going to briefly talk about what work is. Work is going to be the force acting over a distance. And so think about it as like pushing a block up a hill, right? It's going to take some energy to push that over a distance. Even if it's a shelf in a room, it takes energy to move that shelf from one place to another. So you do have to, it does involve that transfer of energy, okay? And that's really the main stuff to know. I'll show you a little bit of the math, but it's not really much of anything to worry about for you. Okay, so let's move on. So temperature, remember, is a property that reflects the random motion of the particles of a substance. And so we do know that temperature is going to be the average of the substances. And so when we're looking at this, we do need to remember that it's not the energy of each individual particle. It's the energy of that substance overall, because we know that we're going to have some particles that move very slow and some particles that move very fast. But in average, that average will tell you where the majority of your particles are going to be. Okay. Now, we do have transfer of energy, right? We've talked about that. But there are two types of transfer here. We've got exothermic, which is going to be when we have that reaction a chemical reaction where it actually releases energy, so releases heat. And so the energy is going to flow out of the system. The potential energy is changed to thermal energy. And then the products are going to have a lower potential energy than the reactants. And how I've always remembered this is exothermic is exit. So that tells me that the energy is exiting that system. It is exiting that reaction. Okay? And so as a result, your surroundings would get warmer. This would be what we would see on a potential energy diagram with an exothermic reaction. So your reactants would start high, your products would end low, so you would see that that heat is leaving, so your change in energy is going to be a negative change in energy. Okay? Then I've got my endothermic reactions, and so endothermic's the opposite of that. Endothermic's where we absorb heat, and that energy is going to flow into the system, so from the surroundings to the system, versus exo would be from the system to the surroundings. The thermal energy is changed to potential energy. Why? Because it's being absorbed in, so it's being stored. And then those products are going to have a higher potential energy than the reactants. And I've always remembered this by endo is enter. That's just how I've always remembered this. And then this would be our potential energy diagram of that. So your reactants start down low, they absorb a bunch of energy, and we would get an endothermic reaction there. Okay, so then heat was absorbed. Now, thermodynamic quantities always consist of a number of a positive or negative sign, and that's telling us if we've gained or lost energy. Now, I will say this is a caveat. If you're an engineer or if you're going into the field of engineering, engineers are going to use their surroundings as the point of view instead of the system. Okay, and so just remember in chemistry, we use the system as our point of view. Okay, now, endo and exothermic. Exothermic, we are going to be a negative heat. Okay, and that's going to be that system energy is decreasing. It's being released into the surroundings. Endothermic, that energy is entering it, right? And so it's going to have a positive change in heat there. And so our system is going to be increasing in its energy. So processes of endothermic and exothermic reactions. So during a lab, a student is asked to make a 2 molar solution of hydrochloric acid. The teacher starts with concentrated 18 molar hydrochloric acid and dilutes it using distilled water. As a result, the student notices the volumetric flask used got very hot. The student claims that this is because the reaction is exothermic, which caused the heat to flow into the volumetric flask. Is the student accurate? Why or why not? So I want y'all to pause your video, take a second, try to solve for this problem. All right, so pause your video, and then I will go over it here in just a little bit. Okay, so hopefully y'all went through and solved this, but if you did not, so here is your answer. It says, so yes, the student is accurate in their claim. Exothermic does tell us that the energy is leaving the system, which is causing the surroundings, the volumetric flask, to warm up. Okay, and so that would be an accurate statement. So its statement would be true. Okay, so this one I'm going to leave as practice for y'all. It will be on the key though, so you can go back in and double check your answer there. All right, so one last page here on the notes for today, and then we will be done. All right, so energy diagrams. So we've already looked a little bit at those potential energy diagrams, but I did want to go a little bit more into depth just to make sure y'all really understand what's going on inside of them. So an energy diagram, which is again also called a potential energy diagram, is going to plot the energy change that occurs during a chemical reaction. So it's looking at that chemical reaction as a whole, and it's seeing how that energy changed from where we started at the reactants and to where we ended at the products. Okay. Now remember that an endothermic reaction, you're going to have your products higher than your reactants, and then for an exothermic, your products are going to be lower than the reactants. You do need to know the parts. So first off, if I were solving for the potential energy of the reactants, I would end up looking right here. Whatever number is there, that's going to be what the potential energy of the reactants is. And they will also tell you the unit that you're using, okay? For my products, again, we would just kind of take this, we'd go all the way across, and I'd be like, okay, well, that would be the potential energy of my products. And then to find my change in heat, I would do my products minus my reactants, and that would be my change in heat there, okay? And do make sure that you're doing your products minus your reactants, okay? We also have our activation energy. Remember, that's the energy that's required for the reaction to even begin to start, okay? I like to think of this as me rolling a ball up a hill. If I don't make it all the way to the top, what happens? Well, the ball will roll all the way back down, and nothing will really occur other than the ball rolling back down the hill, so that excess energy would be released. But if I make it all the way to the top and push it over the edge, then it's going to roll down and the reaction is going to begin, and you'll see your product start to be produced, okay? So do keep that in mind, that your activation energy is what we have to, the amount of energy that has to be added to that reaction before the reaction will even begin to occur, okay? Now, some reactions occur naturally, right? And they're going to be taking energy from the surroundings. So they'll be taking energy from the air or from the table it's sitting on or whatever it is. They might have already met their energy requirement for the reaction to occur, okay? All right, so let's take a look at, sorry, it's kind of being wonky right now. All right, so looking at this, I've got, there we go, I think it's fixed. I've got two practice problems here. So I'm going to do this first practice problem with y'all, and then I actually want y'all to do that second one. So first off, it says, what is the potential energy of the reactants? On the diagram to the left. So these would be my reactants. These would be my products. So then the potential energy of the reactants would be 20 kilojoules per mole. What is the potential energy of the products? Again, we take this, we do kind of a dashed line until we get over to here. So we have 50 kilojoules per mole. So what is my change in heat? Well, I take my products, 50, minus the reactants, 20, and I would get a total of 30. So the change in heat is 30 kilojoules per mole. And so this, in this case, it would be a positive 30, right? What is the activation energy for this? Well, remember the activation energy is the energy required before the reaction begins. So it's going to be based off of your activated complex here. So it's looking at how much energy does it take to go from my reactants to that activated complex. So my activated complex is at about 100. My reactants are at 20. So the difference there would be 80 kilojoules per mole. And then I ask you to draw the effect of a catalyst on this reaction. So looking at this reaction, remember a catalyst is going to be anything that's going to lower your activation energy, right? And so what it's doing is it's essentially lowering your activated complex. And so we're going to take this, and this would be the effect of a catalyst. And they didn't tell us what we added. They didn't tell us how much it changed the activated complex. But what they did tell us is that they added that catalyst, and that tells you that your activated complex and the activation energy is going to be less. And so that's really all I wanted you to signify here. And then last question here is this reaction endo or exothermic? So endo or exothermic, I look, my reactants are lower than my products, so I ended with more energy, which means this is an endothermic reaction. Okay, so here I want y'all to pause your video and start answering this question. Now, here's something I will say. First off, this should be a 2, Okay, so change that 3, that exponent of a 3, to a 2. Second of all, it doesn't tell you what your activated complex or anything like that is. And so you're just going to kind of use your own best judgment. Remember that your activated complex does need to be over those products, okay, and the reactants. But otherwise, I want y'all to pause your video and go ahead and give that a shot. All right. All right, so what do I do here? So looking at this, I've got my reactants and my products. I do need to make sure my axes are labeled. So on the left there, I have my potential energy, which was in kilojoules per mole. And then on the bottom there, I have my reaction pathway. I know my reactants started, so the initial energy of the reaction is 120 kilojoules per mole. And then what I saw is that we had a change in heat of positive 280 kilojoules per mole. So I took 120, I added 280, and that got me up to 400. So I know my reactants started at 120, my products ended at 400. And then I did need to show that my activated complex was above that. And so that's what you see there with that hump at the top, where the activated complex is about at 480. The effect of the catalyst would be it would lower that activated complex, and then your activation energy would be the difference between my reactants and the activated complex. All right, y'all. So that is it for our notes today. As always, let us know if you have any questions, but otherwise, y'all have a great rest of the day. Bye, y'all.